What if the very fabric of our universe, from the most abstract mathematical truths we grapple with, all the way to the most tangible physical phenomena we observe every day, what if it didn't just exist, but emerged from a single foundational principle? And what if that principle could be distilled into something as seemingly simple, yet, well, deeply mysterious, as 0 to the power of 0 equals 1? Welcome to the Deep Dive. This is where we take your sources, your articles, your research, and yeah, our own notes too. We unearth the most fascinating nuggets of knowledge. We try to give you that shortcut to being truly well-informed. Today, we're embarking on, well, it's a pretty mind-bending exploration of the ontology of mathematical physics. It's a revolutionary framework proposing a unified theory for everything, rooted in this concept called coherence generation. We've got a dense stack of material today, folks, outlining a deeply intricate and ambitious vision for reality.
Indeed. And our mission today is really to comprehensively structure and communicate this detailed framework. We're going to unpack a groundbreaking theory that doesn't just describe reality, but suggests how it's fundamentally generated, continuously maintained, actually. This deep dive will guide you through a layered architecture, revealing how mathematics and physics, they're not separate disciplines at all. No, they're interconnected expressions of an underlying coherence. And this approach, it seems to resolve paradoxes that have frankly stumped thinkers for centuries. Our goal here is to illuminate this intricate, unified framework so you can truly grasp its profound implications. See how everything from fundamental particles right up to the structure of space-time might be unified under this single elegant idea.
Okay, let's unpack this grand vision then. Prepare for some serious aha moments, because what we're about to explore, it really challenges some of our most basic assumptions about the universe.
Right.
So our journey begins with what might seem like a simple equation, maybe something you argued about in math class. Yet it's presented here as a bold foundational assertion. 0, 0 equals 1. The source material claims this isn't just a mathematical convention we've sort of adopted for convenience. It's the fundamental axiom of this entire framework. So could you start by telling us why this isn't just a trivial detail, a footnote in algebra? Why is it the coherence-generating invariance axiom for this whole new paradigm? That sounds significant.
It does sound significant, yeah. And what's truly fascinating here is that this isn't merely presented as a proof within an existing mathematical system. That's not the claim. Instead, it's presented as the very principle that defines the system itself. Our sources explicitly state it's the, and I'm quoting here, underlying source from which structure, order, and law emerge.
Oh.
Yeah. So this fundamentally redefines the ontological status of mathematics. It suggests mathematics isn't just discovered, out there waiting for us or invented by humans as a tool, but is, in a really profound sense, self-manifesting through coherence principles. It proposes that mathematics begins with this inherent principle of coherence, rather than relying on, say, arbitrary axioms that, well, as history shows, might lead to inconsistencies down the line. It's a fundamental shift, really, moving from assumed foundations to a self-generating one.
Okay, so if I'm following you, this implies something really deeply significant for the very origin of mathematics itself.
Mm-hmm.
Traditionally, right, we've wrestled with whether math is out there for us to discover the Platonic ideal view or purely a human invention, just a tool we've crafted. This 0, 0 equals 1 axiom, it seems to suggest a third way, like an intrinsic generative capacity. What does this mean for that long-standing debate?
Precisely. You've hit it. This axiom, it encodes self-referential generation, the very essence of emergence. Just think about it for a second. Instead of starting from pure zero as like a void or an empty set, which, has traditionally led to paradoxes in set theory, for example, 0, 0, 0, 1 establishes an invariant foundation. This means that even in a null state, a zero state, the potential for coherence is preserved. It generates unity from nullity without contradiction. It sort of elegantly resolves these issues by showing that zero isn't merely an absence of quantity, but it's a potential coherence generator. The source calls it the irreducible source because it encodes self-generation, unity, and coherence emergence in a single expression.
Huh.
It's like saying that even in what appears to be nothing, there's an inherent instruction set for something to become one, for a coherent unit to just emerge.
That's quite an audacious claim for such a small equation, moving it from, a debated convention to the bedrock of all reality.
Yes.
Given that, can you give us a concrete example? How does this coherence invariance resolve a long-standing mathematical, undefined case? Because in classical algebra, we've just accepted certain expressions as undefined, and that's kind of the end of the story.
Absolutely. Let's consider classical algebra's indeterminate forms. These are often called undefined cases, right? Things like 0 divided by 0, or infinity minus infinity, or 0 raised to the power of infinity. In this framework, they don't lead to inconsistencies or these fundamental breaks, these discontinuities. Instead of just being labeled undefined in this framework, 0, 0, 0 resolves to what's called a coherence equilibrium state.
Okay, what does that mean?
Well, imagine a perfectly balanced system, maybe opposing forces canceling out, but not into nothingness. Instead, into a stable, non-zero state of dynamic equilibrium, like a perfectly tuned resonant frequency that emerges from otherwise conflicting oscillations. This new coherence attractor isn't arbitrary. The claim is it's the only stable configuration that maintains the system's overall coherence. And similarly, infinities aren't treated as just runaway values, but as coherence gradients that stabilize at coherence invariance. The key idea is ensuring that coherence is conserved across all transformations. This prevents these fundamental discontinuities in mathematical structures. It offers a smooth, consistent mathematical reality, which is, yeah, quite a departure from how these cases are conventionally just handled and labeled as indeterminate.
That's a profound reinterpretation, turning what we basically considered mathematical dead ends into points of dynamic equilibrium. Okay, this raises an important question then. If this single axiom provides such a stable, universally coherent foundation, what was the need for a new mathematical and physical paradigm in the first place? Why couldn't we just, continue with our existing frameworks? Hashtag the need for a unified coherence framework.
Well, the need arose because modern physics and mathematics have, frankly, hit conceptual walls. Walls that seem, well, insurmountable within their current paradigms. We have these unresolved paradoxes lingering in areas like set theory, quantum mechanics, especially the notorious measurement problem, that's a big one. General relativity has its singular points, black holes, the Big Bang singularity, and even foundational issues in information theory. These aren't just minor glitches, right? They are fundamental inconsistencies that really limit our ability to provide a truly unified and coherent framework for reality. Our sources highlight that classical formulations rooted in axiomatic assumption, probabilistic interpretation, or structural abstraction have reached their limits in unifying the most fundamental aspects of reality. These persistent inconsistencies, they point to a missing principle, something fundamental we haven't grasped yet.
So if I'm understanding this correctly, the existing approaches, the ones based on, axiomatic assumptions or probabilistic interpretations like in quantum mechanics or structural abstractions, they've essentially reached their limits. Is that fair? They can describe parts of reality, sometimes with astonishing precision, yeah, but they can't connect the whole picture into a single seamless tapestry. They leave us with these fundamental gaps.
Precisely. That's exactly the problem this framework aims to solve. This framework, the Unified Coherence Theory of Everything, or UCTE, it steps in to provide that deeper foundational principle. It postulates coherence selection as the fundamental organizing principle of the universe.
Coherence selection.
It's a bold claim, absolutely. But it offers a systematic way to bridge these long-standing gaps. It provides a foundational logic for mathematics, quantum mechanics, field theories, cosmology, and even, as we'll see later, AI. The UCTE aims to ensure that fundamental structures remain coherent and self-consistent across all scales, from the tiniest quantum fluctuations up to the largest cosmic structures. And it does this by deriving them from this single invariant principle. It suggests that reality isn't just consistent because it happens to be, but because coherence is its generating principle.
Okay, this is where it gets really interesting and quite ambitious. How does this UCTE actually work? How does it build from that single axiom that 0 to the power of 0 equals 1 as a coherence generating principle to describe, well, everything? What's the architectural blueprint, so to speak, of this unified coherence theory? The paper describes this framework as having a layered architecture. Okay, that sounds like a grand design for reality itself. Can you walk us through the 4 interconnected layers of this ontology of mathematical physics? Give us a sense of how they fit together.
Right. Think of it as a progressive symmetry reduction, or maybe a step-down process. It moves from the most abstract, unified principles down to the concrete, observable structures of our universe. And these layers aren't just descriptive categories, you see. They are seen as generative. The principle of coherence is preserved at each step, but it takes on a more differentiated form as you go down. So the 4 layers are: 1. Omnilectic mathematics. This is the most foundational layer. Universal invariance, the ultimate source of order, you could say. 2. Hololectic mathematics. Here, those invariants from the omnilectic layer start to manifest as continuous fields. It's the first step towards physical manifestation. 3. Relational mathematics. This layer focuses on localized dynamics, interactions, and periodic behaviors within those fields. And 4, derived mathematics. Finally, we get to the quantized, discrete systems, the world of particles, and specific measurements that we directly observe.
Okay, omnilectic, hololectic, relational, derived.
Exactly. And the framework also emphasizes what's called mathematical hierarchy versus ontological reduction. It's not just about different types of math we're talking about here. It's presented as a hierarchy of emergence, where increasingly complex structures arise naturally from these foundational invariants, always, crucially, maintaining their underlying coherence.
And this layered structure, this hierarchy, it mirrors what the sources call the big emergence framework in physics, right? Connecting it to cosmic and mathematical evolution. Wow, that's quite a scope. It suggests that the evolution of mathematics isn't separate from the evolution of the universe itself, but like deeply intertwined. Okay, let's dive into each layer then. Let's see how that unfolds, starting at the absolute beginning, the most fundamental layer. Hashtag deep dive into the 4 layers. Hashtag 1, omnilectic mathematics, universal invariance.
Okay, layer 1, omnilectic mathematics. This is the most foundational layer. It represents invariant unified principles in hypersymmetry and coherence. Crucially, the claim is it exists independent of the universe and preceding the big emergence.
Independent of the universe.
Yes. Serving as the hyperspace context from which the universe and its mathematical structures emerge. So it's not just about the early universe, but about the source of all symmetry and invariance, operating at a level even more fundamental than space-time itself.
So it's like the primordial soup, maybe,
Yeah.
of all mathematical possibility, the ultimate blueprint for all that can be before it actually manifests in our reality. Could you expand on what all mathematical possibilities means here? Are we talking about every single theorem imaginable, or is it something more fundamental, like potentialities?
That's a captivating image, the primordial soup. And yeah, in this context, all mathematical possibilities refers more to the entire manifold of potential mathematical structures and relationships. But in their most undifferentiated and unified state, it's not about specific theorems yet. It's more about the absolute unbroken patterns of symmetry and coherence from which all specific mathematical structures will eventually emerge through this process of symmetry reduction. The sources call it the absolute mathematics and hypersymmetry, where all mathematical truths exist in a coherent, unbroken state. Its key properties are universality, encoding all possible mathematical structures within an undifferentiated state, like the potential for every melody existing within a single fundamental vibration. Invariance, governed by immutable principles like conservation laws and fundamental symmetry operators. These are the laws that simply are, regardless of observation or context. And absolute coherence. This means perfect alignment of all components, no internal contradictions, no fragmentation, a state of pure undivided order.
Okay, what are some examples of these universal invariants? Things that are just fundamentally true, sort of regardless of our specific universe. How do they manifest here in this omnilectic layer?
Well, think of the fundamental symmetry groups. Things like SUN, SON, U1, which, are foundational to gauge theories in physics. In this framework, these aren't just abstract mathematical constructs we invent. Within omnilectic mathematics, they represent the absolute unbroken patterns of symmetry that pre-exist the physical universe.
So SU3, for the strong force.
Exactly. In this layer, SU3 isn't just the group for the strong force. It's the primordial pattern of strong coherence from which the actual strong force field in the next layer down will emerge. It emerges through a specific symmetry-breaking event, yet it still preserves that initial coherence pattern. Similarly, Lie algebras like SU2, which generate continuous symmetries, belong here. Universal constants like the speed of light, c, Planck's constant h, the gravitational constant g, they're modeled as invariants from this layer. Fixed coherence parameters, essentially. Even fundamental mathematical constants like pi and Euler's number would reside here, encoding the geometry of circles or exponential growth in their purest pre-emergent form. And Noether's theorem, the one linking symmetries to conservation laws. That also originates here, representing a universal principle of coherence preservation through transformation.
And how does this incredibly abstract layer, existing, as you said, even before the universe, how does it connect to physics as we understand it? It seems to operate on such a meta level.
Yeah, it does. It reflects the undifferentiated hypersymmetry of the early universe, or perhaps more profoundly, the hyperspace context that is the source of all symmetry and invariance, even before the big emergence. Our sources describe it as the coherent resonance fields of hyperspace before symmetry reduction. So it's the ultimate invariant within this big emergence framework. It's the deep structure, the underlying order from which everything else will eventually flow. Hashtag 2, hololectic mathematics, continuous fields. Right, moving down from that purely abstract onelectic layer, we get to hololectic mathematics. This is where the unified invariance of onelectic mathematics manifests as continuous field-like structures. It bridges the abstract coherence of the onelectic layer with the more emergent relational systems that come next. It serves as the first level where those ultimate invariants begin to differentiate into structures that start to resemble physical reality.
Okay, so the abstract principles from homoelectrics start to take form here as smooth, continuous fields, like maybe the quantum fields or gravitational fields we hear about in physics. It's where the blueprint starts to become a kind of flowing medium.
Exactly. Hololectic mathematics is where those utterly abstract blueprints from the omnilectic layer start to take on a more fluid form, you could say, manifesting as continuous fields. If the omnilectic is the blueprint for an ocean, maybe the hololectic is the ocean itself, a vast continuous medium, where the potential for waves, currents, and whirlpools, which become more concrete in later layers, is now present, governed by smooth, unbroken dynamics. Its properties include continuity, describing smooth, continuous structures like fields and manifolds, encoding relational dynamics as differentiable, holistic entities. No breaks or discrete jumps here. Holism, modeling entire systems and their interplay where the whole is greater than the sum of its parts. The system is understood as an integrated unit. And preservation of coherence. This is crucial. The intrinsic order inherited from the onelectic layer is preserved and expressed through these continuous fields, ensuring their fundamental consistency.
What are some examples to help us visualize this? It still sounds quite abstract, even with the ocean analogy. How do these continuous mathematical fields actually relate to physical reality?
That's a good question. Imagine the Riemann curvature tensor in general relativity. It describes how space-time is curved by mass and energy. That's a classic tensor field, defining the geometry of space-time itself. That's hololectic. Or consider a four-dimensional space-time manifold itself a continuous fabric. Gauge fields, like the electromagnetic field, which govern fundamental forces, are prime examples too. These aren't just mathematical descriptions in this view. They are the continuous fields that permeate space and mediate interactions. Hilbert spaces, which are central to quantum mechanics for representing system states like L2R, for wave functions, they fit here as continuous state spaces. Even differential operators like the Laplacian, which describe how fields change and behave dynamically, are part of this layer. These are the mathematical constructs that describe continuous interconnected systems. They represent the first step in the actualization of that universal coherence.
And in terms of physical context, then, how does this bridge manifest in the observable universe? Where do we actually see this layer at play?
This layer corresponds directly to the field-like structures that govern physical interactions and continuous phenomena. So, think electromagnetic fields, gravitational fields dictating the fabric of spacetime, and the quantum fields that particles are thought to be excitations of. It's truly the bridge between hypersymmetry and emergence, where universal coherence begins to differentiate into forms that govern continuous dynamics. It's essentially laying the groundwork for all forces and interactions. Hololectic mathematics embodies the field of potentiality transitioning into active relational systems. It aligns with the idea that the universe operates as an integrated system, maintaining its underlying order even as it differentiates. ###3, relational mathematics, localized dynamics and interactions. Okay, moving further down the hierarchy, we reach layer 3, relational mathematics. This layer focuses on relationships, transformations, and interactions within coherent systems. It introduces localized, oscillatory, and periodic behaviors, but in a purely mathematical sense first, without necessarily requiring direct physical oscillations just yet. This is where the emphasis shifts from those holistic continuous fields to specific dynamic relationships between components.
Ah, okay. So this is where the interplay starts to become more apparent, where things begin to connect and interact in a dynamic way rather than just existing as a big continuous field. This feels like where forces and movements truly take shape, mathematically at least.
Precisely. This is where the universe's internal dynamics really start to unfold mathematically. Its refined properties include localized relationality, focusing on specific relationships between components like mappings or geometrical connections. It emphasizes the connections themselves rather than just the individual entities. It's about how parts relate to each other within a coherent system. Abstract periodicity, describing periodic, cyclical, or resonant behaviors mathematically. Think periodic functions or harmonic analysis, but without necessarily implying a physical wave just yet. It's the mathematical pattern of oscillation or repetition. Interconnectivity, maintaining coherence across related entities. Interactions here must preserve compatibility with their hololectic origins, ensuring that even as parts interact, the overall system remains fundamentally ordered. And it also involves symmetry, preservation, and reduction. It inherits symmetries from the layers above, but now they're expressed as relational transformations, meaning symmetries are either preserved in these interactions or are systematically reduced in a coherent, predictable way.
Can you give us a few examples of this abstract relationality, where these dynamics play out mathematically, showing how these connections manifest?
Certainly. Fourier analysis is a core example. It decomposes complex functions into a series of simpler harmonic components, right? Revealing underlying periodic relationships. That's relational. Wave equations, like the standard Dirichlet, phonetically describe periodic behaviors that arise from interdependencies within a field. That's relational too. Graph theory, modeling networks and connections also fits here. The edges define relationships between nodes in a system. In quantum mechanics, wave functions and their superpositions and entanglement, these define relationships between potential states or non-local connections. These are key examples of relational dynamics, even things like Lagrangian mechanics. It derives system dynamics by minimizing action, highlighting relational principles, the relationship between kinetic and potential energy, rather than focusing on individual forces. It's all about how elements are linked and influence each other dynamically.
Okay, so it's really about the underlying mathematical structures that govern dynamic interactions and connections, forming the basis for phenomena like wave mechanics or the intricate dance of quantum interactions, where components are fundamentally inseparable. ####4. Derived mathematics, quantized discrete systems.
And finally, we arrive at layer 4, derived mathematics. This is the layer of discrete, quantized, or symbolic representations. This is the ultimate step down in the symmetry reduction process, translating the continuous fields and relational dynamics of the upper layers into finite, measurable forms. This is where the universe becomes concretely observable, quantifiable, and accessible to our instruments and our counting.
This truly sounds like the world we directly observe and measure, doesn't it? The world of individual particles, numbers, the specific outcomes of experiments. This is the realm we interact with daily.
It is indeed. This layer represents the culmination of that coherence-generating process, resolving into the familiar discrete units of our reality. Its properties include quantization, reducing continuous dynamics into discrete, countable entities like particles, integers, or eigenvalues. But importantly, coherence and symmetry are said to be preserved even within these discrete frameworks, ensuring their internal consistency, symbolism, and representation, encoding systems in abstract, manipulable forms. Think algebraic equations, matrix representations, symbolic logic. This is how we represent and manipulate information about the discrete world. Discrete coherence. Retaining coherence despite the discreteness. Ensuring that derived systems remain consistent with their foundational principles and don't suddenly become contradictory or nonsensical. And practical utility, forming the fundamental basis for computation, measurement, and symbolic reasoning in applied mathematics and physics. This enables all our technological advancements.
What are the most common examples here that we would recognize? Things that really jump out as discrete and measurable.
Okay, think of number theory. Especially integers and modular arithmetic are fundamental counting systems. That's derived. Eigenvalues and eigenvectors in linear algebra. They represent quantized states in systems like the discrete energy levels of an atom or the spin of a particle, +12, -12. Derived. Combinatorics, the study of discrete arrangements and probabilities vital for understanding things like particle distributions, derived. Algebraic structures like groups, rings, and fields, which define the rules for how these discrete entities combine and operate, derived. Finite graphs and matrices representing discrete relational data in networks, crucial for computer science, derived. Even the discrete Fourier transform, DFT, which converts sample data into discrete frequencies for digital signal processing. Or cellular automata like Conway's game of life, modeling emergent behaviors using simple, quantized rules, all derived.
And in physics, this would be our particles, right? And the specific measurements we take, the actual clicks on our detectors.
Exactly. It corresponds to observable and measurable phenomena, like individual particles, electrons, photons, quarks, lattice systems in condensed matter physics, and of course the digital representations that underpin all computation and data storage. It represents the culmination of symmetry reduction, where continuous and relational coherence resolves into these discrete units accessible to human observation and technology. It's the final output, if you like, of the big emergence process, but still carrying the imprint of the universal coherence from which it originated.
Okay, this layered structure is incredibly detailed on its own. It paints a picture of reality unfolding from abstract principles all the way down to concrete particles. But the truly revolutionary part, I think, is how these layers actually connect and transform into one another. How does the big emergence, as the sources call it, truly play out through these mathematical transitions? How does it seamlessly link these seemingly disparate realms?
Right, the transitions are indeed crucial, and they're not portrayed as arbitrary. They are governed by strict principles: symmetry reduction, coherence preservation, and resonance. And these aren't just, abstract ideas floated out there. They are formalized using the tools of functors and commutative diagrams in
Hmm.
category theory that provides the rigorous mathematical framework needed for such a claim.
Functors and commutative diagrams.
Okay. Yeah, think of functors as mathematical mappings that preserve structure when moving from one category or layer, in our analogy, to another. And commutative diagrams ensure that coherence and consistency are maintained across these transitions. They basically show that different paths or sequences of transformations between mathematical states always lead to the same coherent outcome. This guarantees a mathematically robust and consistent emergent process.
That sounds like a powerful way to ensure consistency. Okay, let's walk through some key examples of these transformations, starting from the most abstract step down. How does omnilectic become hololectic?
Right, so here, universal invariants from the omnilectic layer manifest as continuous fields in the hololectic layer through this process called symmetry reduction. This is the first, most fundamental step of differentiation, where that pure, undifferentiated potential starts to take on actual form. For instance, take those universal symmetry groups we mentioned, like SU3 for the strong force or SU2, SU1 for the electroweak force, which exist as these absolute patterns in the omnilectic layer. They emerge as specific gauge fields, like the strong interaction field or the electroweak field in the holectic layer. These are the fields that mediate particle interactions. The Lagrangian density, which is the mathematical object describing the dynamics of the system, it transitions from a highly unified hypersymmetric form to one describing these distinct fields. But critically, coherence is always preserved through this reduction. This is how, according to the theory, abstract symmetries give rise to the fundamental forces we observe as continuous fields in our universe. They break their initial perfect symmetry, but in a very specific, ordered, coherence-preserving way. It's presented as a structured unfolding, not some random event.
Okay, so the ultimate symmetries yield the fundamental force fields. Then how do we get from those continuous fields to more localized interactions, hololectic to relational?
Next step down. Yes. Continuous hololectic fields differentiate into localized oscillatory interactions described by relational mathematics. This is where the dynamics and relationships within systems become explicit, where the continuous field starts to exhibit specific patterns of interaction and behavior. Let's consider a few compelling examples of this differentiation the scientists give. Example 1. Electromagnetic fields to waves. Maxwell's equations, right? They reside in the hololectic layer, describing the continuous electromagnetic field AC. They give rise to oscillatory solutions for the electric E and magnetic B fields. And what are those? Electromagnetic waves. These waves, with their specific frequencies and amplitudes, represent localized dynamic interactions described by relational mathematics. The field isn't just static, it's now dynamically interacting and propagating.
Okay, that makes sense. From the field potential to actual waves.
Exactly. Example 2. Spacetime curvature to geodesics. You have a differentiable manifold with a metric tensor that's a hololectic construct, describing the continuous curvature of spacetime. This yields geodesics. Geodesics are the paths objects take through that curved spacetime, like the trajectory of a planet around a star. These geodesics are described by relational mathematics. They encode the dynamic relationships of motion dictated by the abstract curvature. The abstract curvature now dictates precisely how things move and interact.
So the continuous geometry leads to specific paths of interaction.
Right. And example 3, Hilbert spaces to wave dynamics. Operators within a Hilbert space, that's a hololectic representation of the continuous state space of quantum systems. They produce relational dynamics in the form of time-evolving wave functions. These are the solutions to equations like the Schrödinger equation. They describe the probabilistic and interactive behavior of quantum entities. These wave functions then define probabilities and interactions between potential states, moving from a static space of possibilities to active, time-dependent relationships.
Okay, so continuous fields give rise to waves, paths, and quantum dynamics. Now for the final step, how do these relational dynamics become discrete things we can count, relational to derived?
Yes, the final step, quantization. Relational dynamics, like wave interference or those topological properties we discussed, are quantized or symbolized into discrete entities in derived mathematics. This is the crucial process that gives us measurable individual things, the particles, the numbers, the specific states we can actually observe and compute with. Let's look at several illustrations of this crucial quantization step. Example 1, wave functions to particles. A quantum wave function, that's a relational concept, right? Describing probability amplitudes and interference patterns across a continuous space. Upon observation, it collapses into discrete eigenstates or individual particles. These particles possess quantized properties, specific energy levels, spin, charge. So the continuous wave of probability becomes a definite particle we can count and measure, a singular point of coherence, perhaps, in a vast field of potentiality. The infamous measurement problem, reframed as quantization.
In a way, yes. Example 2. Fourier transform to discrete Fourier transform, DFT. Continuous wave functions, described by relational Fourier analysis, which breaks functions into an infinite series of harmonic components. They are quantized into discrete frequency components derived via the DFT. This is absolutely crucial for digital signal processing. It converts a smooth, continuous signal into specific, countable frequencies that a computer can process digitally. We go from a smooth, infinite spectrum to specific, countable frequencies.
Right, like MP3 compression relies on something like that.
Essentially, yes. Example 3, topological spaces to quantized invariance. Topological properties like loops or knots in a continuous space that's relational, describing the global connectivity of a space. These are quantized into discrete invariants like Chern numbers. These then describe phenomena in, say, topological insulator, derived, giving discrete measurable properties to abstract topological features. It's like a way of counting the holes or twists in a mathematical structure.
Oh.
And one more. Example 4. Graph theory to adjacency matrices. A graph, G, VE, that's relational, describing network connections abstractly between vertices and edges. It gets discretized into an adjacency matrix, derived. This matrix is a finite symbolic form that allows for computational analysis of the network, representing complex relationships as a countable table of ones and zeros.
Okay, so if I'm understanding this correctly, the real elegance here lies in this seamless flow. Even as symmetry is reduced and forms become more concrete, more discrete, the core coherence from that initial 001 axiom is always preserved, right? That's the key. So it's not just a description of static layers, but a dynamic generative process, from the most abstract universal principles all the way down to the individual particles we can actually measure and interact with. Am I capturing the essence of that unfolding?
You've captured it perfectly. It's presented as an unbroken chain of coherence. The UCTE provides, or aims to provide, a consistent, mathematically rigorous explanation for how the universe unfolds. From its most fundamental invariant principles to the complex, diverse reality we inhabit. Each transition is portrayed as a carefully orchestrated process of coherence selection and symmetry reduction, always ensuring that the underlying order is maintained. Creating, in theory, a truly unified and self-consistent reality. Hashtag reinterpretation of fundamental physics through the UCTE.
Right. Now, this framework isn't just a philosophical construct or a mathematical exercise, is it? It promises to resolve some of the most stubborn, long-standing paradoxes in physics by fundamentally reinterpreting core concepts. Let's start with quantum mechanics, a field famously full of strange, counterintuitive phenomena like superposition, entanglement, the measurement problem. How does the UCTE tackle these quantum enigmas?
It really does propose fundamental redefinitions for several aspects of quantum mechanics. It moves away from purely probabilistic interpretations towards a reality seemingly driven by an intrinsic order. First, quantum superposition. In this framework, wave functions aren't just probability distributions. They're treated as coherence-preserving structures. This implies quantum collapse isn't random or arbitrary, but a selection effect from hypersymmetric coherence states.
Selection effect, meaning?
Meaning it's less like a roll of the dice and more like a specific frequency or hypersymmetric coherent state being selectively amplified and stabilized from a vast field of potentials. And this selection happens through the act of observation or interaction. The observer then, rather than passively collapsing a wave function randomly, acts as a dynamic coherence modulator, influencing which coherent state is selected and actualized into a definite outcome, one that's consistent with the universe's underlying coherence principles.
Okay, that's a very different view of the observer's role. What about entanglement? Smooky action at a distance.
Entanglement, yeah, this gets reinterpreted too, not as mysterious, spooky action at a distance, but as a coherence conservation process. Specifically, it's described as a bivector coherence state. This new understanding attempts to explain the instantaneous correlation without requiring faster-than-light information transfer, because it's fundamentally a shared non-local coherence, an intrinsic connection that persists across space and time, maintaining the system's overall order. It's like two parts of an original, undivided coherent state that remain linked.
Interesting. And the quantum vacuum, that sea of virtual particles.
Quantum vacuum states. The zero-point field, usually seen as this bubbling sea of virtual particles popping in and out of existence, it gets redefined as a coherence background state. This means vacuum fluctuations aren't just random noise, they're actual manifestations of coherence interactions within this background state. This elevates the vacuum from just empty space to a foundational state of coherence potential, potentially driving emergent phenomena.
And the Schrödinger equation itself, the core equation of QM.
Schrödinger equation. Even this cornerstone gets derived from coherence invariance. The wave function is treated as a coherence-preserving function. This crucial shift makes quantum states coherence-selected rather than fundamentally probabilistic. It adds a layer of intrinsic determinism rooted in the preservation of coherence rather than relying solely on inherent randomness.
That's a profound shift, definitely, suggesting an underlying order even in the quantum realm. Now, what about the other pillar of modern physics, general relativity, our understanding of space, time, gravity? How does the UCTE reinterpret something as fundamental as space-time itself and the forces that shape it?
In general relativity, the UCTE also makes some profound redefinitions that tie directly back to this idea of coherence. Space-time, it's redefined, not as a passive stage or arena, but as an active coherence field. Its metric, the thing that measures distances, is described as dsisc dx plus oitek plus dzc bas tan dt, where c is explicitly a coherence function. This means spacetime isn't a fixed background, but a dynamic field that emerges as a function of coherence stabilization. Its geometry reflects the underlying distribution and flow of coherence.
So space-time itself is an emergent property of coherence.
That's the proposal. And relatedly, Einstein field equations. Gravity itself is treated as a coherence function. This implies that spacetime curvature is not an independent phenomenon, but an emergent result of coherence flow across hyperdimensional layers. So what we perceive as gravity, the bending of spacetime by mass and energy, is viewed as a direct manifestation of underlying coherence dynamics, a drive towards local coherence equilibrium.
And things like time dilation, clocks ticking slower when moving fast.
Time dilation. Yes, relativistic effects like time dilation and length contraction get explained as a coherence shift. Mathematically, maybe something like TO angle CV, where CV is a coherence function dependent on velocity. These aren't seen as arbitrary metric distortions, but as coherence-induced transitions that maintain the system's overall consistency as it moves through different states of coherence. It aims to offer a more fundamental, unified explanation for these observed phenomena, rooting them in this coherence principle.
Okay, so it reframes both quantum mechanics and general relativity.
Yeah.
How does this framework then contribute to our understanding of the universe on the largest scales? In cosmology, does it address mysteries like dark matter, dark energy, the beginning of the universe?
It certainly attempts to. It proposes a comprehensive, coherence-based early universe emergence model. Dark matter, for example. It's hypothesized not as some exotic, totally unknown particle, but perhaps as a coherence-selected neutrino condensate, offering a novel, coherence-driven explanation for its elusive nature.
A neutrino condensate.
And the perplexing vacuum energy discrepancy, one of the biggest unsolved problems in cosmology, where theoretical predictions and observations are wildly off. This framework suggests a resolution via hypergravity coherence, where the vacuum's energy is a dynamic property of coherent hyperspace interactions, not just a fixed value. And cosmic evolution itself, the expansion and structure formation of the universe, is seen as being dictated by coherence dynamics, not just entropy, implying an underlying drive towards greater coherence organizing the universe's evolution.
Wow. Okay, you also mentioned information theory earlier, which is increasingly seen as fundamental to physics, especially with concepts like the holographic principle. How does coherence play a role in information and its preservation?
Right. In information theory, the UCTE provides critical reinterpretations that aim to bridge it directly with physics. Shannon entropy, the standard measure of information uncertainty or disorder, gets redefined in terms of coherence preservation. This implies that what we perceive as information loss might actually be coherence-driven redistribution rather than purely probabilistic decay. It's about how coherence is conserved and rearranged. And this framework also offers a potential resolution to the black hole information paradox, another major unsolved problem where information seems to just vanish when it falls into a black hole. The UCTE asserts that information is coherence preserved rather than truly lost. It suggests the coherent states are just redistributed, perhaps across different layers or dimensions of this framework. Information, viewed as a form of coherence, cannot be destroyed, only transformed or relocated within the overall coherent framework of reality. #hashtag applications in AI, information theory, and technology.
This all sounds incredibly foundational, yeah. Reinterpreting the very laws of the universe. But beyond these deep theoretical implications, what about practical applications? What doors does this open, especially in cutting-edge fields like AI, advanced computing, maybe future technology? How can this deep theoretical framework actually translate into real-world innovation?
Well, according to the sources, the UCTE could potentially open doors to entirely new domains, promising revolutionary advancements that might fundamentally reshape technology. For instance, AI decision-making. Instead of current AI optimizing primarily for probability or pattern matching, the idea is coherence-based AI selects decisions that maximize coherence across multiple input gradients.
Maximize coherence. How?
It means the AI wouldn't just pick the most likely answer based on past data, but the one that best harmonizes all available data and constraints into the most internally consistent state. This could lead to AI systems that are more stable, resilient, robust, and make more holistic, intrinsically consistent decisions, perhaps avoiding some of the brittle or contradictory outcomes we see now. Then there are coherence neural networks, CNNs. These are envisioned as next-generation AI models where the neural nodes maintain coherence memory, preventing information loss or degradation across processing layers. This could allow AI to process information more holistically rather than in fragmented steps, addressing a major limitation of current deep learning. Imagine an AI that truly understands context and underlying relationships without needing massive retraining.
That would be a leap.
Absolutely. And quantum AI via coherence selection. This paradigm suggests using quantum coherence selection to optimize AI behavior directly within quantum computing. The goal stated is error-free quantum computing through coherence conservation principles. By leveraging the universe's supposed intrinsic drive for coherence, this could allow AI to harness quantum phenomena more effectively, pushing past current limitations.
Error-free quantum computing, that's the holy grail.
It is, which leads to coherence-preserving quantum circuits. This suggests proposals for entirely new quantum computing architectures, circuits that would use coherence conservation principles to inherently eliminate decoherence errors, directly tackling one of the biggest hurdles in building robust, scalable quantum computers. Instead of constantly fighting quantum noise and errors, you'd design systems that naturally maintain coherence.
And beyond computing, any other predicted technologies?
Yes, the framework predicts the potential design of intelligent systems, synthetic intelligence systems, that are not just artificially intelligent, but inherently coherent in their operations. It points towards hyperdimensional resonance engineering for novel forms of communication, sensing, and maybe even propulsion, leveraging these principles of coherence across higher dimensions. And it even suggests coherence-based energy extraction using concepts like coherence engines and hypergravity.
Coherent engines. Hypergravity.
Yeah, imagine advanced communication systems leveraging these principles for incredibly efficient, perhaps entanglement-enhanced, and error-free data transfer, or new energy sources that somehow tap into the very coherence of space-time itself. Speculative, of course, but part of the vision.
That's truly groundbreaking territory. It connects the most abstract mathematical principles and reinterprets the fundamental nature of the universe, all while pointing towards potentially powering future technology and intelligence in ways we can barely imagine right now. It paints a picture of a future deeply intertwined with these coherence principles, moving from pure theory to potentially tangible innovation. #Haj philosophical implications and addressing challenges. Okay, expert speaker, this framework is undeniably ambitious. It's presenting a complete re-envisioning of reality. What are its broader philosophical implications? And how does it address the long-standing challenges in the philosophy of mathematics, where thinkers have debated the nature of mathematical reality for centuries?
Well, philosophically, it positions mathematics as both a descriptor and a generator of physical reality. That's a monumental shift right there. It suggests mathematics isn't just a tool we happen to use to understand the world, but is inherent to the structure of reality and reflects universal laws, actively participating in its manifestation. This provides what the sources call a unified relational absolute duality, suggesting mathematics is both absolute in its foundational principles, that omnilectic layer, and relational in its emergent forms, the hololectic, relational derived layers.
So it's a unified vision. But how does it stand against traditional ontologies in mathematics, like Platonism, formalism, or structuralism? Each of those offers a different view of what mathematics fundamentally is. Does this framework pick a side, or does it somehow manage to integrate or transcend them?
The claim is that this framework transcends them by offering a more integrated hierarchical approach, weaving together aspects of each. It finds resonance with several views. It aligns with Platonism in that the absolute mathematics and hypersymmetry, that omnilectic layer, resonates strongly with the idea of mathematical truths existing independently in some timeless abstract realm prior to any physical manifestation, the unchanging ideals.
Okay, so it has a Platonic element.
Yes. It incorporates structuralism through relational mathematics, the third layer, which echoes the focus on relationships between entities, rather than the entities themselves as being the core of mathematical understanding. The patterns and connections are key. It accommodates formalism and nominalism with the derived tertiary layer. The fourth layer, which emphasizes human-constructed abstractions and symbolic systems. This recognizes the practical utility and conventional role of human-defined mathematics, but grounds it in a deeper reality. Intuitionism constructivism finds resonance in the emergence of relational mathematics through symmetry reduction, which can be seen as a constructive process where mathematical structures are built up from simpler, coherent principles. Empiricism is addressed by a relational mathematics' ability to precisely describe physical systems, directly tying mathematical structures to empirical observation and its application to the physical world. And finally, universalism is deeply embedded. It strongly aligns with mathematics reflecting universal laws, providing a concrete mechanism, this layered emergence for how they manifest, rather than them just being an abstract coincidence.
So it sort of incorporates elements from all of them.
Exactly. Crucially, it fosters this unified relational absolute duality, bridging seemingly opposing philosophical views by showing how they might represent different layers or perspectives within a single coherent framework. It's not about choosing one, but seeing how they all might fit into a larger dynamic picture.
That sounds like it integrates the best of these philosophies while providing a dynamic process-based view of reality, an evolutionary ontology maybe. But what about Gödel's incompleteness theorems? Those famously suggest inherent limits to any formal system, implying that not all truths can be proven within a given system. How does this framework, which aims for ultimate coherence and unity, handle that profound mathematical challenge?
That's a critical point, absolutely. And the framework aims to sidestep some of the pitfalls of self-reference, highlighted by Gödel. How? By proposing that mathematical truths are ultimately grounded in hypersymmetry reduction, which acts as a kind of metasystem existing outside the conventional formal system of mathematics as we usually define it.
A metasystem.
Yes. By modeling mathematics as this dynamic emergence through symmetry reduction, it introduces a temporal and causal component. It avoids treating mathematics as just a static, self-contained system subject to Gödel's constraints. This external axiomatic basis in hypersymmetry, residing in the omnilectic layer, provides a foundation that isn't itself reliant on internal proof within a single formal system. Therefore, the claim is the overarching system can be complete and consistent without running into Gödel's limitations, because its ultimate ground lies beyond the self-referential paradoxes of any single isolated formal system.
Okay, that's a clever way to approach it, grounding it externally. And the use of category theory with functors and commutative diagrams, how does that solidify this framework? How does it provide mathematical rigor to such a grand layered vision, especially in light of these deep philosophical and logical challenges?
Right. Category theory provides the rigorous mathematical formalism needed to represent these layers in their transitions with supposedly unparalleled precision. Category theory emphasizes relationships they call them morphisms over individual objects, which aligns perfectly with the relational nature of this ontology, where the connections are just as fundamental as the entities themselves. Functors formally describe the symmetry reduction process. They act as mappings that preserve the underlying structure when translating objects and transformations between categories, for example, mapping from the hypersymmetric absolutes of the omnilectic layer down to the relational systems of the third layer. Commutative diagrams, in turn, ensure coherence and consistency across these transitions. They visually and mathematically demonstrate that different paths or sequences of transformations between mathematical states always lead to the same coherent outcome, regardless of the order you perform the operations. This provides a robust structure, aiming for an almost irrefutable proof of coherence preservation and consistency throughout the entire emergent hierarchy. It gives the UCTE a powerful mathematical backbone.
Okay, so what does this all mean for us? For the learners out there trying to grasp the ultimate nature of reality, what's the big takeaway from this incredibly deep dive into a potential unified theory of everything? Hashtag outro. Fanjoy.
Well, I think this deep dive reveals a universe potentially not built on arbitrary assumptions or disconnected laws, but on a single elegant principle of coherence generation, a principle that unfolds through this breathtaking, layered continuum, from the invariant hypersymmetry of analectic mathematics through the continuous fields of holectic, the dynamic interactions of relational, down to the discrete, observable structures of derived mathematics. It's presented as a unified, elegant, and powerfully generative framework. It shows that mathematics, in this view, is not just a tool for description, but an inherent active component of reality itself, right from that foundational moment of 0 to the power of 0 equals 1.
And it's an intellectual journey, isn't it? One that offers a pathway to potentially resolve some of the most profound scientific and philosophical questions that have, haunted humanity for centuries. And simultaneously, it points towards potentially revolutionary advancements in fields like AI, energy, and maybe even our understanding of consciousness itself. It's a testament to the idea that the universe might be far more interconnected or coherent than we ever imagined, with mathematical principles driving its very existence and evolution, from the smallest quantum fluctuation right up to the largest cosmic structures.
Absolutely. This is a framework that truly positions mathematics as the fabric of reality, not just a tool we use to describe it. It invites you, the listener, to consider how every aspect of existence, from quantum foam to cosmic structures, might resonate with this underlying coherence, this intrinsic order that defines what is possible and what emerges. It offers a fresh lens, really, through which to view the universe, one that promises, or at least hopes for, a new era of integrated scientific discovery by seeking the patterns of coherence in everything.
So here's a provocative thought for you to mull over after this deep dive. If all of reality fundamentally emerges from coherence, how might our own human understanding and pursuit of coherence in our science, our technology, perhaps even our philosophies, how might that evolve to unlock the next era of integrated scientific discovery? And maybe, just maybe, even reshape our perception of consciousness itself. Thank you for joining us on this deep dive into the ontology of mathematical physics. We hope this exploration has given you a powerful new lens through which to view the universe and its incredible, possibly hidden order. Until next time, keep exploring, keep questioning, and keep diving deep.